Exponential functions are really common in chemistry. You've just seen the Boltzmann distribution in statistical thermodynamics. First thing to notice is that exp and e raised to an exponent are just two ways of writing the same thing. The partition function is an example of a sum of exponentials. Exponentials are also common in reaction kinetics as rate laws and in the Arrhenius equation. They also come up in classical thermodynamics as in the Van 't Hoff and Clapeyron equations. You'll run across these later in this unit of study. Using these equations is easier if you remember generally how to manipulate exponential functions and how to deal with complicated exponents. The Boltzmann equation is an example of something with a pretty complicated exponent. Minus e to the ei minus e naught all divided by kBt. We can write this as e naught minus ei all divided by kBt, or as e naught over kBt minus ei over kBt. So we can simplify it overall as a ratio ni star divided by n naught star, we'll call that y, as the exponent of a minus b, or equivalently e to the a minus b, where a is the ground state energy E naught divided by kBt, and b is an excited state energy EI divided by kBt. How does this help? Basic rules for manipulating exponential functions are the same no matter what the exponent looks like. So we have e to the a plus b is the product of e to the a and e to the b. E to the minus a is 1 over e to the a, and e to the a minus b is e to the a divided by e to the b. This means we can express the Boltzmann distribution as ni star equals n naught star e to the difference of energies divided by kBt, or as n naught star times the ratio of two exponents, e to the e naught over kBt divided by e to the ei over kBt, or as negative exponents, n naught star times e to the minus ei over kBt divided by e to the minus e naught divided by kBt. All these versions of the Boltzmann distribution are equivalent. This makes the maths of worksheet 3 much simpler to take an example. If we take the ratio ni star over nj star, the occupation numbers of two arbitrary energy levels in the most probable distribution, we write that as a Boltzmann distribution n naught star e to the minus energy difference divided by kBt divided by n naught star e to the other energy difference for ej divided by kBt. And we want to simplify this. First we cancel the ground state occupation numbers. Then we write each of those energy differences in the exponent as a ratio of two energies, e to the minus ei over kBt divided by e to the minus e naught over kBt in the numerator, and then do the same thing in the denominator. Now at this point we can cancel out e to the minus e naught over kBt in the numerator and the denominator, or we can rewrite it as the product of e to the minus ei kBt, ei over kBt times e to the e naught over kBt in the numerator, and a similar thing in the denominator using our inverse rule, e to the minus a equals 1 over e to the a. We cancel it now, and that leaves us with a simple ratio e to the minus ei over kBt divided by e to the minus ej over kBt. That can now just be recombined into an energy difference in the exponent. Using the same rule, e to the a minus b is e to the a divided by e to the b. Now the same rules for manipulating exponential functions can be generalized. Exponent of e to the a plus b plus c plus d plus etc. is equal to e to the a times e to the b times e to the c times e to the d, etc. It's not e to the a plus b plus c plus d equals e to the a plus e to the b plus e to the c plus e to the d. They're not equal to each other. Let's not see that again. Similarly, e to the a plus b minus c minus d, we can combine those rules to give us e to the a times e to the b times e to the minus c times e to the minus d, or e to the a times e to the b divided by e to the c times e to the d. Now we'll use these kinds of relationships later to simplify some molecular partition functions when we get further into the unit of study.